All right, so today's talk is called The View from Above. And we're going to be telling you guys all about satellites and the way satellites can be used to study Earth from above. So to start off with, let's have a brief discussion on what satellites are. They are any object that orbits a celestial body. These can be natural satellites, like for example, the moon is a natural satellite of Earth, or Earth itself is a natural satellite of the sun. Today, we're going to be particularly focusing on artificial satellites, which is machinery that orbits a celestial body. And these can be used for a number of different purposes. For example, you guys are probably familiar with the Hubble telescope and JWST. Those are both satellites that are used for astrophysical science. And satellites can also be used for science on Earth. So that can be meteorology, studying climate change, um, studying tides and tectonics. And Laith is going to tell you more about that in his section. And these satellites can come in a large range of sizes. So these satellites can be as big as a football field, like the International Space Station, or they can be as small as a Rubik's Cube. These smaller telescopes are called CubeSats. They're really efficient ways for scientists to study things such as climate change or to do Earth imaging, and also to test new technology, like, for example, different propulsion systems. These are kind of hard to keep in orbit just because they're so tiny and you can only put so much technology on them, but they are a really cheap way of sending a lot of scientific devices to study out in space. Okay, so in this next bit, we're going to go do a brief history of satellites, starting with the beginning of the space race, which was July 29th, 1955. Now, this is a very specific date because this was the date that the US first announced that it was going to send up the first satellite in the next couple years. The space race was a period of the Cold War that was marked by significant advancements in intercontinental ballistic missile technology, which would be very helpful for sending up satellite, and also got a lot of the public involved. Like there was a lot of propaganda posters from both the U.S. side, which is like this one here and the one in the far corner, and also on the Soviet side, which you can see here in white. I've put the translations of what those posters say. So the next step in the space race is the start of the International Geophysical Year. This was a period in 1957, which was also known as the Third International Polar Year. Now, the polar years are these events that happen pretty infrequently, where there's a lot of international collaboration to do as much study as possible on Earth's polar regions. The first one was held in 1882. There have been several held since then, one recently in 2007, and a future one is going to be planned in 2032. This particular polar year was also nicknamed the International Geophysical Year because the focus of it was the space race. Go back. Okay. So the reason that this particular time was chosen for the International Geophysical Year was because it was at the peak of solar cycle 19. Now, a solar cycle is a roughly 11-year period of the sun going through increased and decreased periods of activities. We measure this activity by the number of sunspots we observe on the sun. So you can see here, the tracking of solar cycles goes about to the 1750s. And you can see here that 1957 roughly corresponds to the peak number of sunspots observed during solar cycle 19. The reason that they want it to be during the peak period of a solar cycle is because they thought there would be a lot more interesting science that they could get out of by studying the solar wind. We now know that it's actually not a great idea to send up satellites when there's peak solar activity because they can interfere with our ability to communicate with them. But we didn't know that at the time. All right. So the next step in our timeline is October 4th, 1957, which is the launch of Sputnik 1. This was a Soviet satellite. The name Sputnik in Russian just means satellite. It only managed to stay in orbit for a few months before it returned to Earth's atmosphere. But through communication between the satellite and Earth, the scientists were able to learn a bit about Earth's ionosphere. And you can see, I'm not going to try the pointer again. And you can see this that all Sputnik 1 was just the sphere with all these antennas sticking out. Those were for radio communication. All right, so in Sputnik 2, we're not going to go too much into this in this talk, but one of the goals of the space race was to eventually get a person on the moon. And to do that, scientists kind of had to understand, all right, what are conditions like in space? How does being in space affect a living person? What kind of things do we need to protect them from? And so as a precursor to eventually sending people into space, they sent animals into space. And on Sputnik 2, this was the first spacecraft to carry any animal into space. And this animal was a dog named Laika. Now, sadly, Laika was sent on Sputnik 2 without the expectation she would survive it. And she was unfortunately put through quite a bit of unethical training to get her ready for it. She was put in increasingly smaller and smaller cages so that when she's in a very cramped satellite, she won't like freak out or move around. They also put her in a centrifuge to get her used to experiencing G-force. Nowadays we might not engage in animal testing like that, but at the time the ethics of this was just kind of like, nah, okay, we just want to get something out as fast as possible. Unfortunately, she passed away from hyperthermia not long after she got into orbit, which means it got too hot for her. And it's her actual cause, like what caused her to pass away, is not quite known, but it's believed part of it might be the shielding between the capsule and the rocket sending her into space didn't separate properly or didn't separate at the right time, so it got too hot for her and it caused her to pass away. All right, so I don't know why the photos aren't showing up. Okay. Uh, Next, we have the launch of Explorer 1. This was the first US satellite that was sent up in February of 1958. Last contact with it was in May of 1958, but unlike Sputniks 1 and 2, it managed to stay in orbit for until about the 1970s. And the reason these satellites were kind of dying after a few months was because we weren't using solar power to keep the batteries charged on them. So after a few months, it would just eventually die. And also on the bottom here, I put a picture of the computers who calculated Explorer 1's orbit. These were mostly women who were hired to do calculations that nowadays we might use a computer for. They don't get a lot of recognition in history, so I wanted to give them a shout out. All right, so Explorer 1 led to one of the most significant discoveries in the International Geophysical Year, and that was of the Van Allen radiation belts. These are regions of charged particles from the solar wind that get trapped by Earth's magnetosphere, and they form these, there's like four permanent belts, which you can see. There's the inner one, outer one, they're kind of horseshoe shaped. Occasionally there can be transient ones. I think there was one in 2013 that lasted a few weeks, but these four tend to stay all the time. And the way that scientists knew that there was something there was that on Explorer 1's cosmic ray detector, they noticed that depending on what part of Earth's orbit Explorer 1 was at, it would detect a different concentration. And some points it would be a lot, some points would be none at all. And the one thing that the Van Allen radiation belts do for us is they also not just trap particles from the solar wind, but they also protect us from it. When these particles get trapped, they also can deflect additional solar wind particles and cosmic ray particles, which, if we didn't have it there, would eventually ablate our atmosphere. So good that we have them. All right. So that's a brief history of satellites. So now, where are satellites today? The amount of satellites that are orbiting Earth today are a little bit uncalculable. There's estimates that range from about 11,000 to 19,000. There's some that are going up. There's some that we might lose contact with. There's some like tiny CubeSats that might stay up for a while but then fall back into Earth. And they exist in several different layers of orbits around Earth. I'm going to go through a few of them now. So the first one is low Earth orbit. Most satellites that are used for for science are in low Earth orbit. And this is an area that's less than 1,200 miles from Earth's surface. Most satellites exist in around 400 to 800 miles from Earth's surface. These orbits also have an eccentricity of less than 0.25. Eccentricity is just a measure of how round or how ovally an orbit is. So eccentricity of 0 would be a perfect circle, and then going all the way to 1 would be like a parabola. Their maximum orbit time is about 128 minutes, which means they travel at speeds of roughly 15,000 to 18,000 miles per hour. For example, the International Space Station is in low Earth orbit. It's about 248 miles from Earth's surface, and it makes about 15 and a half orbits a day. There's also a website you can look at to see if the International Space Station is traveling over you. And the fun thing about low Earth orbit is, aside from the Apollo missions in the 60s and 70s, no human carrying spacecraft has actually traveled beyond Earth orbit. Every other one that has gone before and since has been within low Earth orbit. But that is going to change next year. The Artemis 2 mission is going to take 4 astronauts on a 10-day fly-around mission to the moon. And that will be the first time in almost 50 years that any human has left low Earth orbit. So one particular category of low Earth orbit is a polar or sun-synchronous orbit. And most Earth observation satellites that are in low Earth orbit are in nearly polar orbits. This means that the axis of the orbit has roughly an 80 to 90 degree angle with the equator. They're at altitudes of roughly 430 to 500 miles, and on average about 100 minutes for one orbit. Now, what I mean by sun synchronous is that whatever place on Earth that the satellite is passing over, it's going to be the same local time. So for this example, I've said, all right, it's 3 o'clock wherever this satellite is passing over Earth. Another interesting thing about polar orbits is these orbits also precess at the same rate that Earth revolves around the sun. And what I mean about precession is, if you look at this GIF here, this is of the sun and Earth, but let's pretend this is Earth and a satellite. The point of closest approach of the orbiting object to the object it's orbiting moves over time, and eventually it'll make a whole circle and go back to where it began. We call that one full precession. And for a polar orbit, it would take exactly 1 year. Next type of orbit I'm going to talk about is a geostationary orbit. These orbits are only one orbit per day, and they're fixed at 22,236 miles in altitude. And the reason for this is because geostationary orbits are meant to basically have a fixed position relative to Earth. So if a satellite was, say, right over Milwaukee, for example, no matter what point of the year it is, what time of day it is, it's always going to appear that it's just staying over Milwaukee. And one interesting thing about geostationary satellites is they can also cover a much larger area of Earth, which means like their signal can be detected on larger areas of Earth than, say, low or medium Earth orbits. So you can see in this visual here, the geostationary satellite can cover about 30-ish% of Earth's surface, as like the low and medium Earth orbits would need a lot more satellites to cover the same area. I will hand it over to Leith.
All right. Thank you, Lulu, for taking us through how these satellites work in their orbits. I'm going to go through all of the cool Earth science that we do with Earth observation satellites. Now, there's a lot, and we won't have enough time to cover everything that they do today, but we will hit some of the major players. And these include what we can learn about the atmosphere, from how it moves to its composition, as well as Earth's long-term climate. We'll also look at how satellites help us study the Earth's water cycle, as well as the Earth's biosphere, which encompasses all life on Earth, from terrestrial to aquatic life. And then we will explore how satellites study the Earth's surface and interior. And then finally, we'll look at how they track and monitor human activity. So researching for this talk was a fun but challenging task because I had to learn about all of these topics and then combine them down into around a 20-minute portion of a talk. But one thing that makes it easier is that all of these topics are very deeply connected, and it's impossible to talk about one or to study one without studying another. And this is because Earth is essentially just one complex interrelated system of all these different areas. Then because of this, these areas require a lot of collaboration between different sources to properly study. So you need to combine data from various types of satellite sensors, as well as observations taken from the ground or the upper atmosphere. And this integration and combination of data from different sources in this field is known as data assimilation. And there are entire offices dedicated to assimilating satellite data. This graphic here shows weather observations being assimilated into NASA Goddard's Earth Observing System, also known as GEOS 5. So each color represents um, a different source. So like light blue represents observations from the ground, but we also have infrared, microwave, and radio observations from satellites. And one impressive product of this data assimilation, and one of the best predictors of weather, is measuring aerosols. And let's see if the video play. Okay. So this is the visualization of aerosols. Aerosols are these tiny particles in the atmosphere that are many times smaller than the width of a human hair. And we can actually characterize different aerosols based on the wavelengths of light that they emit or scatter. This is called spectrometry, and it's used a lot in astronomy for measuring the elements of distant objects in space or space dust. And in this visualization, the red represents black carbon aerosols, which mainly come from wildfires. And if you look at around Canada, you'll see a few, and in recent years, those have been the cause of a few air quality alerts we've had here from smoke or haze drifting down from these wildfires. The purple represents mineral dust, which come from deserts. So they're most prominent in the Sahara Desert, and they can even blow across the Atlantic Ocean into the Americas. And then the blue represents sea salt aerosols, which are blown up into the atmosphere from ocean spray. And by tracking sea salt aerosols, we can measure and track the formation of intense weather events like hurricanes. And restart the video. And then finally, we have the green, which represents sulfates. These come from volcanic activity, as well as emissions from burning coal or other fossil fuels. So by tracking the amount of sulfates in the atmosphere, we can track volcanic activity as well as human emissions. And like I said, aerosols are a great predictor for weather formations and weather patterns. And in this case, weather refers to any process that occurs on a local scale all the way up to a global scale. And it also includes any processes in the atmosphere that happen from the scale of minutes all the way up to an entire season. And while aerosols are a great predictor of weather, we have to use many things to get good predictions, like looking at cloud patterns and cloud systems, as well as measuring the surface temperatures of both the land and sea. We also look at rainfall distribution, as well as snow and ice cover. So this image here shows Hurricane Milton, which formed last year in October. And Hurricane Milton went from a tropical storm all the way up to a category 5 hurricane. And the intensification of this hurricane was partly predicted by measuring the rise in surface temperatures using the satellite NOAA 21. So this satellite goes on a polar orbit, like Lulu talked about earlier, and it orbits the Earth around 14 times per day. And it has infrared sensors which measured this rise in surface temperature. And hurricanes need high enough sea temperatures to both form and intensify. So this rise in surface temperatures reflected and contributed to a short-term intense weather event like this, but it also reflects a more long-term shift in Earth's overall climate. And climate satellites measure global changes, like the Earth's total surface temperature, as well as global melting of glacial ice, as well as sea level rises. And from data and observations from climate satellites, we can create models like this, which compare the human and natural drivers to climate change. This is an example of how we measure ice melting with satellites, or changes in sea ice. Oh, it's not showing. There we go. Okay, so this shows an overlay of um, many images of Antarctica and Greenland that were used to track the change in ice thickness per year. So the red represents where there has been loss in ice, and then the blue represents where there's actually been accumulation of ice. And this was made with data from NASA's ICESat-2 satellite, which specializes in observing glacial activity. Now, the melting and accumulation of sea ice also contributes to the water cycle, which is very important for satellites to study because it helps us manage natural resources, as well as tracking where water shifts and moves across the planet, from things like precipitation to river runoff to soil moisture levels. And one satellite that tracks this kind of thing are NASA's twin GRACE satellites, which orbit together on a polar orbit. And over the course of a few years, they measured a rapid loss of freshwater reserves in the Middle East. So this is a close-up of part of the Euphrates River, and it shows a rapid loss of river water from pumping. So the water was pumped by humans much faster than the natural water cycle processes could replenish it. And measuring the water cycle isn't just important for managing our natural resources, but it's also vital for um, plant life and vegetation, which brings us to another important cycle known as the carbon cycle. And this is driven by the biosphere, which I mentioned earlier encompasses all life on Earth. So when ecosystems change, it affects the atmosphere's ability to store nutrients like carbon and nitrogen. So by measuring the color of reflected light, satellites can determine how successfully plant life is photosynthesizing, which gives us a good sense of things like ocean chlorophyll levels and land vegetation. One example of this are presentation. Okay, there we go. One example of this is phytoplankton blooms. So phytoplankton are these microscopic marine algae, and they're the base of the marine food chain. And this is a true color image of a phytoplankton bloom, which happens when um, nutrient-rich cold water comes to the surface and mixes with sunlit surface water, and then the phytoplankton just explodes in population and and causes this kind of thing to happen. So phytoplankton blooms actually account for nearly half of all the photosynthesis on Earth. So just by looking at the color of the oceans, satellites can give us a good indication of Earth's overall carbon budget. Another big contributor to the carbon cycle is the Amazon rainforest. So we use satellites a lot to track the deforestation in the Amazon. This image here is of deforestation in Bolivia due to sugarcane farming. And this image, as well as the last one, were taken by NASA's Terra and Aqua satellites, respectively. So the Aqua satellite was launched in 2002, and it specializes, as you could probably guess by the name, in measuring the water cycle as well as glacial activity and anything to do with the ocean. And then the Terra satellite is actually NASA's flagship Earth observing satellite. It was launched in 1999, and it studies basically every topic that we've talked about so far, as well as our next one, which is the Earth's surface and interior. So studying the Earth's surface with satellites is fairly straightforward because we can see it directly. And we can actually use these same methods that we use to characterize aerosols to characterize minerals on the Earth's surface. So by looking at them across a range of wavelengths and seeing which specific wavelengths they emit and scatter. And this helps us both in managing natural resources as well as tracking and monitoring things like landslides and volcanic eruptions. We can also see how the crust moves by using satellites to track tectonic plate movement. And we actually gave a great talk on this last semester called Why Does the Earth Get Angry?, which I would recommend checking out on YouTube after this if you haven't already. So tracking tectonic movement helps us monitor and predict places where things like earthquakes or tsunamis are more likely to happen. And interestingly enough, you can also learn a lot about the Earth's interior with satellites. And to do this, you need to employ some pretty clever tricks, one being measuring slight variations in the Earth's gravity. Satellites do this by precisely tracking their own orbits around Earth. And when and variations in gravity are induced by shifts in the mass distribution inside of Earth. So by mapping gravity changes over a long period of time, you can get a good sense of how mass is moving in Earth's interior, which we can then infer properties of the mantle and the core from that. And these are what underlie tectonic movement as well as they drive Earth's magnetic field. And here is a map of Earth's tectonic plates. The blue lines represent the tectonic plates themselves, and then the boxes represent where we have what's called satellite laser ranging data, which takes precise laser measurements that measure the movement of the tectonic plates. And when I say we, in this case, I mean NASA. And the reason the entire Earth isn't covered is for a variety of like political and socioeconomic reasons. But just by measuring parts of these tectonic plates, we can get a good sense of how they move as a whole since they're all connected to each other. And again, it's important to monitor these plates so we know where different areas have a higher risk of events like earthquakes. And we also use satellites to monitor earthquake damage, how it affects landscapes as well as cities like this. So this shows 3 cities in Turkey that were damaged by an earthquake a few years ago, and these were taken by Japan's ALOS 2 satellite, which, just like all the satellites we've talked about so far, also follows a polar orbit. And in addition to monitoring natural hazards like this on communities, satellites also monitor many aspects of human existence, like infrastructure and land use and economics. And one very important kind of satellite for precisely measuring things like this are GPS satellites, or global positioning system. So GPS satellites work um, by timing and yeah, you time multiple satellites to gain an exact position on Earth. So GPS satellites broadcast their exact time down to a receiver, and the receiver uses the time it took for that signal to arrive to measure the distance to that satellite. And by doing that with multiple satellites, at least 4, you can get your precise location on Earth. And this has many uses other than navigation. And I should also mention that receivers have to account for a slight shift in these radio signals due to the fact that satellites they're high enough up that they have slightly weakened gravity, and they also move very fast with respect to Earth, and these induce a relativistic Doppler shift in the radio signals. And so this we actually have to use Einstein's relativity in order to get precise GPS measurements. And GPS isn't just used for navigation, but it's also used to study every topic that we've talked about so far, as well as measuring human activity. And one example of human activity that these satellites measure is this is a study showing global industrial fishing activity. So the blue dots represent where industrial fishing is publicly tracked and publicly reported, and then the red dots actually represent where satellite data had to be used to reveal that fishing activity. And this study found that nearly 75% of all industrial global fishing is not publicly tracked and could only be seen by satellites tracking their activity. So this is very important for linking industrial fishing to things like degradation of aquatic ecosystems and the environment. And we also use satellites to monitor urbanization in cities. So this image here shows a comparison of Las Vegas between the years of 1989 and 2019, and this reflects uh, a nearly quadrupled population size between these years. Satellites can also monitor urban growth and urban activity via looking at the color and brightness of streetlights. This image here is of Berlin. It was taken by ESA astronaut Andrew Kuiper on board the International Space Station. And even though it's been over 35 years since the Berlin Wall dividing East and West Berlin fell, you can still make out a difference between the two halves via the color of their streetlights. This is because before the wall fell, they developed their lighting independently. And so they ended up using different materials and getting different, slightly different colors in their streetlights. And this difference can still be seen today from space. Now, just a few months after the Berlin Wall fell, in February of 1990, the space probe Voyager 1, on its way leaving the solar system, it just passed Neptune. It turned around and snapped what is probably one of the most iconic photos of Earth from space. And here's that photo right now. And you're probably, if you haven't seen this before, you're probably wondering, where is Earth in this photo? I just see a bunch of blurry lines. But if you have seen it, you might be able to make it out in this red circle here. It's just this pale blue dot. Um, so that is Earth seen from nearly 4 billion miles away. And so on that little speck is everyone you know, everyone you love, and everyone who has ever existed. So I think this image is very important because, in the words of Carl Sagan, it underscores our responsibility to deal more kindly with one another, to preserve and cherish the pale blue dot, the only home we've ever known. And with that, our talk is concluded. Thank you for listening.